So, welcome back to lectures on engineering mathematics 2, and this is lecture number 22, and we will continue with the iterative methods for solving system of linear equations. So, in the last lecture we have already developed or derived two methods or two iterative methods. One was the Jacobi iteration method, another one was Gauss-Seidel iteration method. And now we will use these methods to solve some system of linear equations. So, basically using Jacobi method and also using Gauss-Seidel method, we will see how to get the solution of a system of linear equations. So, just to recall, if we have a system of linear equations, let us say A x is equal to b, where this A is an n cross n matrix and x is n cross 1 or the column vector, and b is also a column vector with n components. In that case, what we have seen that iterative methods, both the iterative methods which we have developed or in general the idea of iterative method is to have such a general form where left hand side we have x evaluated after this k plus 1th iteration, and the right hand side we have G, which is called the iteration matrix, and then this x k, which is this is the vector evaluated or used at kth iteration, and then we have some other matrix H into B. So, coming to the Jacobi method, we consider the following the splitting, that if we write A as L, the lower triangular matrix, plus D, the diagonal matrix having entries in the diagonal from the coefficient matrix A, and U is the upper part of the coefficient matrix. In that case, this A x is equal to b can be written as L plus D plus U x is equal to b, and from here we will derive the form of this iterative method, getting this d x together here and taking this L plus U to the right hand side plus this b, and if assuming that D inverse exists. So, we can multiply by this D inverse. So, the right hand side we have D inverse L plus U and D inverse b, and this is precisely the form which we are looking for an iterative method. So, x k plus 1th iteration is equal to g x k and h b. So, here we can now set up the iteration. So, this x we will replace by this x k, then the right hand side we have minus d L plus u, which is the iteration matrix G for this Jacobi method, and then this d inverse is like h there in the general setting. So, this is the Jacobi method written in this matrix form, where this x is a vector and then d is a matrix, here L is a matrix, u is a matrix, x is a vector, d is again a matrix, and b is a vector. Sometimes it is convenient, and we will also see in some numerical calculations, that writing instead of this vector matrix form, this component form is much more convenient. So, this component form is exactly coming from this vector form, because here we have this x having for instance x 1, x 2, x 3 and x n components at this k plus 1th level. And similarly, the right hand side also after this multiplication we will have a vector of same components, number of components, that is n. So, here what we have done, we have just written or compared each component equal. So, the general x I component, which is somewhere here, let us say. So, x I component is written now directly in terms of the coefficient and the other components of x. So, which can be seen directly from here, because this D inverse. So, D is the diagonal matrix having these entries A 1 1, A 2 2, A 3 3, for instance we have 3 by 3 matrix, and then all these components are 0, that is our D, and this L and U are the lower and the upper one. So, L is the lower. So, here we have 0 already on the diagonal, and also on the off diagonal we will have 0 entries. only these terms will survive, that is A21, and here we have A31 and A32, and similarly we have the upper triangular matrix where the next to the diagonal terms will survive, all other will set to 0. So, that is the upper triangular matrix. So, when we multiply this L to x, for instance, if we take here x 1, x 2, x 3, what will happen? We have the first term 0 basically, then A 21 will be multiplied by this x 1, and that is all. In the third case, we have the A 31 and A 32 will be multiplied to this one. So, what is happening now here after this when we take this component. So, here whenever this j is less than this I, then only this summation will take place, because otherwise this will become 0. And similarly, here when j is greater than I, this will be the other way around when we take the upper triangular matrix. So, this sum will be for j greater than I, and then for each row we will compare. So, we will get that the ith component equal to this expression, which is b I, and this d I will just divide each number by the diagonal entries I I. So, here also we have this I I, and also at this place we will get this I I, and this D inverse B will be again this B I vector divided by these diagonal entries A I I. So, this is the component form, and here we have the vector form of the, or vector matrix form of the Jacobi method. And then we have also discussed that once we have this Jacobi method, for instance written in this component form, and from this component form it is very easy now to write the Gauss-Seidel method, because the only difference is in the Gauss-Seidel method, instead of using these xi's from the kth iteration, from the previous iteration, because we are evaluating now at k plus 1th iteration, and we are using all the values of x 1, x 2, x 3, x n from the previous iteration. So, the idea is that instead of using the values from the previous iteration, we can use the recently evaluated values, and that means in this sum basically whenever this j is less than I, by that time these x j's are available from the same iteration, because we are computing, let us say first x 1, then x 2. So, when we compute x 2, x 1 is available, which can be used here in this first summation. So, the only difference is now for the Gauss-Seidel, this k will be replaced by k plus 1, and as a result we have also seen in the previous lecture that this vector matrix form will take place now in this following manner, that x k plus 1 is equal to minus d plus L inverse multiplied by u. So, that will be the matrix G, or the iteration matrix G for Gauss-Seidel method, and then here also this d plus L inverse will come with B. So, these are the forms which we can use, either we can use the component form or we can use the matrix form, whichever is convenient. So, if we take this example now, we consider the following system of equations: 5x plus y plus 2z is equal to 13, x plus 3y plus z is equal to 12, and minus x plus 2y plus 4z is equal to 8, and we want to compute just x 1, the first after this one iteration, using Gauss-Seidel and the Jacobi method. What would be the approximation of Jacobi and the Gauss-Seidel method after one iteration, if we start with the initial guess 1 1 1. So, regarding the convergence of these methods for this given system, we will discuss a little later in the next lecture. So, in this lecture we will just evaluate these approximate values, for instance in this case just after one iteration. So, these are the given equations, the system of linear equations, and we know that the Jacobi method has this form, that 1 over a I I, and then we have b I minus, and here the sum is over j, where j is not equal to I, and it is summed for all other values. To write down the Jacobi method, indeed we do not have to remember this formula, because what this formula says, that the right hand side, for example, we are writing the x 1. So, for x 1 we say that b 1, that is here already, divided by a 1 1, this is a 1 1, these are the coefficients. So, this coefficient is a 1 1, this is here a 1 2, and this 2 is a 1 3, and so on. Here again we have a 2 1, this is a 2 2, and then here 1, this coefficient is a 2 3, and then here we have a 3 1, and then a 3 2, and then a 3 3. So, these are the coefficient matrix which can be written also in this form as this a 1 1, a 1 2, etc. So, having this formula, what we are doing actually, this x 1 is equal to b 1 divided by this a 1 1, and minus again we are dividing by this a 1 1, that is this 5, when we sum with this a I j to x j, and this is nothing exactly, it is a 1 2 and a 1 3, because the sum is over j. So, we have a 1. So, 1 is fixed now, I is 1 for instance to write this equation. So, what we are doing here, a 1 2 x 1. So, x 1 x 2 x 3 in this particular case, x 1 x 2 x 3 in our component settings here represent just simply x y z, because here the notation for unknown is taken as x y z, not x 1 x 2 x 3. So, here this getting this x 1, the first component x, it is like b 1 over a 1 1. So, we have to divide by this 5. So, we will get here 13 by 5, and then minus here the sum. So, a 1 2 with x 1 and a 1 3 with x 3. So, a 1 2 and a 1 3, because when I is 1, j will not be equal to 1. So, precisely this is the number here now. So, 1 into this component and plus this 2 into this third component of this x is used. So, without remembering this formula, what we can do, we can write the Jacobi iteration method. From the first equation, we will take x to this side, and the rest, these two y and z, the other components, will go to the right hand side. So, right hand side we have 13 there, minus this y, obviously at previous iteration. So, here if we are talking about the values at this after one iteration, then these will be the values at 0th iteration, which we will plug into these equations. So, here then minus 2 z and this 0th iteration value. So, this is the first equation, which is exactly the equation we will get from this formula. So, without remembering also, what we will do, we will in the first equation we will set for x. So, x equal to everything will go to the right hand side, and then we will set up this iteration. The left hand side will put 1, the right hand side we will put the previous iteration, that is 0 in this case. Initial guess was taken as 1 1 1. So, if we take the initial guess, so we have to substitute 1 here, and we have to also substitute 1 there. That means 13 minus 1 and then minus 2, that is 10, and divided by 5. So, we will get this value as 2. Regarding the second equation, and again we do not have to really go through this formula, directly we can write. So, from the second equation, now we have to take y this side, and the rest everything. So, x and z will go to the right hand side, and then we will set up the iteration. So, here we will put a 0, then we will put here 1, and the later iterations also, for example, in the second iteration this will be 2, and this will be just the iteration before this, that is 1. Well, so having this, now for y, we can again here we have x 0, z 0, that is the starting values, which are 1 1 in our case. So, we have 1 and 1, that is 2, and 12 minus 2, that is 10. So, we have this 10 by 3, the second component, the approximate value of y after first iteration. In the third one again, so in the third equation now we will write for z. So, that means this 4 z will remain here and minus x plus 2 y will go to the right hand side, and then we will divide by 4 also. So, we have 1 by 4, then the right hand side was this 8, then we have plus this x and minus this 2 y, and then we have set up these iterations. So, the values as 0th level, and the left hand side we have the values after first iteration. So, these are the initial guess which are known to us. So, here we have 1 and minus 2. So, this is minus 1, and then we have plus 8. So, this is all about what we are getting 7 by 4. So, these are the values after one iteration. What will be now done if we want to get iteration in the what if we want to approximate for these 2 iterations, or we want to get values after next iteration. So, these values here now, instead of this 1 1 1, we will now we will use these values in the next iteration. So, for y, for instance, this will be used, for z this will be used, and then we will get the new value after the next iteration. For x, again here this x and z values will be used, x and z from here. Again in this case x will be used as 2 and y will be used as 10 by 3. So, we can apply, or we can use these values which we have computed now to forward our iteration to get the values after second iteration. So, these are the values after first iteration. So, if we want to get for the Gauss-Seidel method, the only difference, again we do not have to remember the formula for the Gauss-Seidel also. The only difference in this Gauss-Seidel and Jacobi would be, in Jacobi we were using for the complete evaluation after this first iteration, for instance, in each, for the evaluation of each component we were using the initial values. Now, here what we will do for x 1, for instance, the formula will remain the same as the Jacobi, there will be no difference. So, from this equation we will write this as x 1 is equal to 1 by 5, and this y minus 2 z will go to the right hand side. So, we will have this iteration scheme, and then we have this 1 by 5 and 13, and since now we have only available values as the starting values, starting guess. So, that we can plug here 1 and then minus 1. So, we have this value as 13 minus 2. So, this is actually 12. So, if we go to the previous step, the value here 13 minus 2. So, this is 11 by 5, and there also it will be as 11 by 5. So, here also we have 13 minus this 2, that is 11, and then by 5. Coming to the next one, when we have this equation for y, and there exactly the difference comes. So, here we have this 2, sorry. So, this is 2 here. So, that is what it is a 10 by 5 only. So, the value is 2. So, this was 2 which was missing there in the earlier case also, it is the same. So, after this first iteration, the value using the Gauss-Seidel as well as using the Jacobi method, we have the same value, because at this stage when we are evaluating this x 1, we do not have any other value than this initial guess. So, if the initial guess is same in both the methods, then naturally this first component will be the same in both the cases. Now, when we come to this y, we have 12 minus, so we have 12 minus this x and minus z and divided by this 3 there. So, here we have slight difference, because now we will be using x 1 which we have just computed here. We will not use these values which are used here for instance in the first evaluation, because x 1 is now known, the x 1 we have a new value. So, that is the difference, that this new value will be used in this evaluation now, and since z 0 is not available. So, we will use of course from the initial guess. So, having this, now we have 12 and then this is 2 there, and then we have 1 there. So, we have the values here 9 by 3. So, this is the number 3 we are getting for y 1, which is different now from the earlier calculations from the Gauss Jacobi method, because in Jacobi method this x 1 was not used, the x 0 was used. So, that was 1 there and we got the 10 by 3, but now we are getting here as 3. Coming to the third equation. So, we will naturally get this 4 z equal to 8 minus or plus this x and minus 2 y, and then this 4 we will divide. So, this will be the setup for the iteration scheme, and now x 1 is available and also the x 2 y 1 is available. So, x 1 is available and here y is also available. So, we will be using these values now, which we have just computed. So, we will not use the values from the beginning, but we will use now the newly evaluated values as 2 here and 3 there. So, that means it is a 2 and then we have minus 6 there. So, 8 plus 2 10 minus 6 we have 4 and by 4. So, we have the value 1. So, these two values are different than the Jacobi method, whereas the first value, because here nothing is available, we have to use the initial guess only, otherwise the formulation is same. So, that is a slight difference, that in Gauss-Seidel method we are using whatever we have available, recently evaluated values available with us, whereas in Jacobi method we finish the complete iteration with the values from the previous iteration. Well, now the question is that if we take this starting guess 1 1 1 again and perform one iteration using matrix form of Jacobi and Gauss-Seidel method for solving system of equations. In the previous example, we have used the component form, which was directly possible from the given equation. From the first equation we have written in terms of x equal to something, then from 3 y equal to, and then 3 was divided, and from the third equation we got z from here. So, this was easy indeed to get these iterations for each component. For x we got from first equation, the iteration for y from the second one, and from for z we got from the third equation. But now we will write everything in the matrix form, because sometimes using matrix form is much easier in many programming languages. Once we have these matrix form, the computation is going to be faster. So, for instance, if we use the Jacobi method, where we need to get this iteration matrix, and the iteration matrix for Jacobi method is minus D inverse and then L plus U. L is the lower triangular matrix, U is the upper triangular matrix. So, our A in this case is 5 1 2 1 3, the coefficient matrix, and then we have minus 1 2 and 4, and the right hand side B vector is 3 12 8. So, having this matrix A, now the diagonal, the D will be having only 5 3 and 4 in the diagonal entries, rest everything 0. So, that means, and that to inverse. So, for the diagonal matrix getting inverse is very easy, we have to just invert the diagonal entries. So, instead of 5 we have 1 by 5, then we have 1 by 3, and then we have here 1 by 4. So, this was the diagonal entries were 4 3 4 5 3 4. So, we got this inverse 1 by 5, 1 by 3 and 1 by 4 with this minus sign, and L plus U. So, L is the lower triangular, U is the upper triangular. When we are adding this, basically it is nothing but A minus D. So, L plus U is nothing but matrix A minus, we remove the diagonal entries. So, removing the diagonal entries, so we have set here 0 0 0 and the rest everything same. So, 1 2 1, here we have 1 minus 1 and 2. So, the rest everything is same. So, we got this minus D inverse and this L plus U, we can multiply these two matrices and we will get a new matrix here, which is our iteration matrix. So, first we need to compute the iteration matrix, and then having this iteration matrix for the Jacobi method, the iteration scheme is that x k plus 1 is equal to g x k plus this D inverse B. This was the iteration scheme written in the matrix form. So, that means, if we take the starting values now this, that is this x k will be replaced by this 1 1 1. The benefit now here in this matrix form, that after just matrix vector multiplication we will get the all components, the value of all components. We do not have to compute one by one. So, here for example, we have the x, y, z, these are the 3 components after this first iteration. How do we get g j, that is the iteration matrix which we have just evaluated. So, this is g j, x k, that is now the starting values we want to use. So, x 0. So, we have this 1 1 1 plus we have here again this D inverse. D inverse means the diagonal entries will be just inverted. So, we have 1 by 5, 1 by 3 and 1 by 4, and then we have 13, 12 and 8. So, that is the right hand side B of our system, of our linear system. So, having this now, we have substituted these x naught here. So, x naught, the starting values, and then we have to just perform this multiplication, and then we have to add it. So, this multiplication here for this matrix and this vector, it is just the addition of these rows. So, 1 by 5 plus 2 by 5 will be minus 3 by 5. Then here also 1 by 3 and then 1 by 3, that will be 2 by 3 with the minus sign. Here also we can add. So, 2 by 4 and then minus 1. So, 1 by 4 with the negative sign. Similarly, here this is just 13 by 5, 12 by 5 and 8 by 4 and 12 by 3 and then 13 by 5. So, this is the vector coming from this product. And now we can add the 2 and we got 2, 10 by 3, 7 by 4, and these are exactly the values which we got earlier also using the component wise calculation. Here the benefit is, once we have this one, we just need to plug this instead of this 1 1 1, and then again these multiplications we will get the next value. Indeed, in this D inverse B there will be no change. So, this vector we can keep as it is. The only change would be in the first multiplication, because this 1 1 1 will be replaced by 2, 10 by 3 and 7 by 4, and then we can get the next update, and so on. We can proceed with this algorithm to get values, our values updated after each iteration. Coming to the Gauss-Seidel method, we have this matrix form minus D plus L inverse U and D plus L inverse. This is the iteration matrix for in this case. So, D plus L now, so basically the lower triangular. So, this is the lower triangular part and plus this diagonal also with the diagonal entries. So, this is D plus L, and then we can get this D plus L inverse. So, here we have the in the 1 over the determinant. So, 5 3 into, so the determinant will be or the determinant of this D plus L will be 5 into 3 into 4, that is 60, and then this is the adjoint of this matrix which can easily be evaluated. For instance, this 12 is coming from this evaluation 4 into 3 and minus 2 into 0, that is the 12, and then for instance, this one here will be coming as 4 minus 1 0 and then the negative sign, because we have to consider plus minus and so on. And for the third one we have 2 and plus this 3, that is the 5 there, and then for instance, for this one we have 0. So, this is 0. For the next one, when we compute for this, we have 20, this is exactly there. Then this one we will compute 10 with minus sign, and then similarly we can compute for this and this. So, we will get this adjoint matrix, the transpose has to be done. So, the D plus L inverse is just after taking transpose of this and dividing by 60, we are getting this D plus L inverse. Having this D plus L inverse, we can plug this into this matrix form. So, we have D plus L inverse, we have this upper triangular matrix, we have D plus L inverse, and then we have this B from the equations, the 13, 12 and 8. And then we need to just multiply this one, x 0 we can take 1 1 1, and so we have this iteration scheme that x k plus 1 is equal to this matrix multiplication with this vector plus this vector, and if we plug this initial guess here, for instance 1 1 1, and do this evaluation, we will get 2 3 1. So, the advantage here in the matrix form is that we have to just do this once. To get this form, we have to do some calculations like inverse and so on multiplication, but once we have this form here, we just need to plug the initial value here, and then for instance this is the value after first iteration, again we will use this there, we will get the new value and so on, and iterations will be very fast. The last problem here, we want to solve this one 4 x 1 2 x 3, and then we have the second equation, we have the third linear equation, and we want to use for instance this initial guess 0.1, 0.8 and 0.5, and we want to perform 3 iterations using this initial guess, and we will use the Jacobi and Gauss-Seidel method to do this. So, the Jacobi method, as usual we discussed before, that from the first equation we will write, or we will set up the iteration for x 1, taking this 2 x 2 plus this x 3 to the right hand side, and this 4 was already there, and then we need to divide by 4. So, we have this iteration for x 1, putting this k there and k plus 1 to the left hand side. Similarly, from the second equation we can perform for x 2 after this k plus 1th iteration, taking this x 1 and x 3 to the right hand side, putting them at kth iteration. From the third equation, we will get this x 3, and this 3 x 1 and 2 x 2 will go to the right hand side with these kth iteration values and so on. So, this is the iterative method, the Jacobi iteration method. We will plug these values, the initial values here by putting k equal to 0, and we will get the values after first iteration. Again, we can move to the next iteration by putting by using these values after first iteration to get the values after second iteration. So, having this iterative scheme, if we start with this initial guess, so x 1, so we will put here for x 2 like 0.8, here we will put 0.5 and do this calculation, we will get 0.475. For x 2, we will plug here x 1 and x 3, from the all values will be used from this x 0 until we get this complete step, or we compute all the components in this iteration. While in the Gauss-Seidel, we will use recently evaluated values as well. So, this is the Jacobi one, we will use again x 1 and x 3 from this initial guess only, that is 1 and this 0.5. So, this value is 1.133, and then to compute this x 3 also we will use the values from the initial guess itself. So, x 1 was 0.1 and then x 2 was 0.5 there, 0.8 there, and then this will give 0.85. And now, in the next iteration these values will be used instead of these 0.1, 0.8, 0.5. So, if we use these values here, we will get the next values of x 1 after second iteration, x 2 after second iteration, x 3 after second iteration, and then if we use these values in this scheme again, then we will get x 1 after third iteration, x 2 after third iteration, and then x 3 after third iteration. Well, so this was the Jacobi method. The only difference in the Gauss-Seidel will come that the first evaluation will be the same, because we will be using exactly the initial guess, while in the second one x 1, this will be used the recently computed values, because now x 1 is available, x 3 is not available. So, we will use still from the previous one, and we will get some different value there. Similarly, in the third component x 1 and x 2 both are available now, and we will be using those recently evaluated values. So, coming to the Gauss-Seidel, that is the only difference, that this x 1 will be here now k plus 1, and this x 1 and x 2 both will be using the k plus 1th values. So, starting with this guess, the same evaluation as in the Jacobi 0.475, and then the next one there will be change here, that x 1 now will use this value instead of the value from the 0th iteration or the initial guess, and this 0.5 naturally will come from this initial guess because it is not available yet, and the value is 1.0083. The x 3, x 1 and x 2, this both the values will be used now from this iteration which we have already evaluated. So, like 0.475 and this 1.10083 will be used now, and we will get a new value 0.5931, and similarly we can proceed for the second iteration. So, all these values from the second iteration, and then we will get the values after the third iteration. So, here there was a difference that the whatever we have evaluated, that value will be used in the current iteration, current evaluation. Well, so that was the evaluation part. In the next lecture, so these are the references. In the next lecture, we will continue with this how to, what is the convergence issues of these two methods, which converges faster, etc. So, here just to conclude, we have evaluated or we have approximated the solution of a system of linear equation using the Jacobi method and also using the Gauss-Seidel method, and we have seen that either we can use the matrix vector form or we can use the component form depending on the convenience. And the major difference in both the methods is the evaluation of this term, for instance. So, here we are using until the iteration is complete, that particular iteration, to get all the components, we are using the values from the previous iteration, whereas here we are using the recently evaluated values. So, that is all for this lecture, and I thank you very much for your attention.